demonstrating Charles' law of gas, which states that there is a direct relationship between the volume and temperature of a gas. This means that as the volume increases, the temperature increases, and vice versa. This is expressed through his formula, V1 over T1 equals V2 over T2, where V1 equals the initial volume, T1 equals the initial temperature, and V2 and T2 are the second volume and temperature. Okay, the experiment we will be doing today is balloon in a bucket, or in this case, a sink. The purpose of our experiment is to show how temperature affects the volume of a gas, to demonstrate Charles' gas law. The materials we will be using is a balloon, a bucket, or in our case, a sink, full of ice water, one measuring tape, a thermometer, a timer, and something to keep the balloon submerged in the ice water. Go.
So we just drew our line around the balloon so that when we measure it before we put it in the water and after we put it in the water, we're measuring the same line just as a reference so that the experiment is controlled. This is our controlled variable. Got to get it right on the line. At 64.5 centimeters, which is 640.5 millimeters. And then we're going to take the balloon and we're going to put it in a bucket, or we have a sink of ice cold water. There's ice in here. And we're supposed to hold it under for 10 minutes, but it gets a little cold with your hands. So we're going to put this bucket on top of it and then hold it down with the other bucket. Or bowl, sorry. And then we're going to put this thermometer in the ice water also, just so that we know the temperature of the water that the balloon is in.
So we will see our balloon in 10 minutes later.
So we finished holding the balloon under the water for 10 minutes. So we're going to take it out and measure the circumference quickly before it goes back to its original size from the temperature change. And make sure you get it on the line again so that you're measuring the same spot that you did before. At 62 centimeters, which is 620 millimeters.
Okay, so while we held the balloon under here, we had a thermometer attached by a string hanging in the ice water so we could get the exact temperature that the balloon was at. And it was at 6 degrees Celsius.
Here we have our official data from the experiment. For our initial volume, we used the circumference of the balloon. We were able to use the circumference of the balloon because the circumference is relative to the volume, so the circumference is 645 millimeters. The initial temperature was 22.2 degrees Celsius, which when you add 273, you get 295.2 Kelvin. Our final volume of the balloon was the circumference of 620 millimeters, and again we were able to use that because the circumference is relative to the volume. For our final temperature, we got 279 Kelvin, or 6 degrees Celsius. But let's say we didn't know the final volume, and we would label that as X. If we didn't know the...
Okay, so to find the theoretical circumference of the balloon, we are going to put V2 as our X, because that's the one that we don't know. So we're going to plug in everything else like we did before. So we would have 645 over 295.2, and then 279. We would then cross multiply, and we would get 295.2x is equal to 100 179,955. Then we would divide both sides by 295.2 to get our x alone. And then we would get x as 600.
Now that we have our theoretical yield, which is 609.6 millimeters, and our actual yield, which was 620 millimeters, we will be able to find our percent yield. By doing this, we put the actual yield over the theoretical yield. The actual yield was 620 millimeters, so we put that over 609.6. When you divide this, you get 1.017, but you have to multiply it by 100 to find the percent, and you get 101.7, which you can round to 102%.